Thank you very much. So the goal of this talk is to discuss some aspects of Perrin-Riou's approach to P-Adic L-functions in a critical slope case. So let me start with a very brief survey of what is known in this situation. So let F be a cuspidal new form of weight K0 plus 2 and level n, and let P be a fixed prime which doesn't divide the level. So we denote by alpha and beta the eigenvalues of Accueil operator at P, and denote by F alpha and F beta the P stabilizations of the form F. So just to fix ideas, let's pick one of these stabilizations, say F alpha. So the goal is to construct by natural way some P-Adic analogs of complex L functions satisfying some interpolation properties. In a non-critical case, this means that the P-Adic evaluation of alpha is strictly smaller than K0 plus 1. It was done in the beginning of 17th by many people, Manin, Vishy, Kamis, Velou. Next, it was revisited by Mazur-Tate, Teitelbaum. So this approach relies on the theory of modular symbols and interpolation properties of P-Adic L functions. So one uses these properties to show that there exists a unique P-Adic distribution of, in some sense, controlled growth, interpolating special values of complex L functions. Later, this construction was revisited by Stevens in terms of his theory of overconvergent symbols. So I won't recall definitions and notations because I need this. I don't need this result in the remainder of the talk, and the goal here is just to give some general idea of the story. So Stevens constructs the space of overconvergent symbols of weight K0 with respect to the congruent subgroup gamma, which comes from gamma 1n, and we add the level P2. And there exists a natural arrow from the space of overconvergent symbols to the space of classical modular symbols. This map is not injective, but if we consider the action of the Atkin-Lehner operator UP on both spaces, and if we consider the slope decomposition and take only the pieces of slopes strictly smaller than K0 plus 1, then Stevens proves that restricted to these subspaces, the map is an isomorphism. So classical modular symbols appear when we consider complex values of L functions. And overconvergent symbols allow to construct P-Adic distributions. And if we can lift a classical modular symbol to an overconvergent modular symbol, when we can construct a P-Adic distribution interpolating P-Adically spatial values given by classical modular symbol. So this is the approach of Stevens. The next case, non-theta critical but critical case, appears when the P-Adic valuation of alpha is equal to K0 plus 1, but the modular form is not theta critical. In this case, already the classical approach fails because we cannot construct by a unique way the distribution of prescribed order growth interpolating special values of complex L-functions in this case. However, the approach of Stevens works. Pollack and Stevens proved that if we consider the generalized Accueil eigenspaces of these spaces of symbols, which correspond to the stabilization F alpha of the form F, when there is so the natural map from overconvergent to classical symbols becomes an isomorphism on these eigenspaces. Again, we can lift the classical modular symbol to an overconvergent one and construct a P-Adic L-function which satisfies the prescribed interpolation properties. The case which we will interested in is the theta critical case, where the P-Adic valuation of alpha is K0 plus 1, and the stabilization of F is theta critical. So in this case, the theorem of Pollack-Stevens fails, and this case was studied by Benois using the geometry by a careful study of the geometry of eigenvariety at this point. Among other things, Benois proved the following. In a theta critical case, the eigenvariety is ramified at the point which corresponds to F alpha over the weight space. The dimension of a generalized eigenspace of space of symbols has dimension equal to the ramification degree of the eigenvariety at this point. So using these results, Benois constructed a two-variable P-Adic L-function which in some sense reflects these structures. However, the interpolation properties of this function are strange and amazing. For example, if we restrict this two-variable L function on the point which corresponds to F alpha, so then this restriction vanishes on the critical strip. But if you consider the derivatives, So in some sense, the high non-zero derivative of this, the first non-zero derivative of this restriction on the critical strip, then its values are related to the values. Sorry, there is a typo here. So the special values of this Belaïch P-Adic L-function is related to the values of P-Adic L-function associated to another stabilization of f to the, with respect to beta. So this is a strange phenomenon, and our goal was to understand Belaïch's construction from the point of view of Perrin-Riou theory and the theory of Euler systems. So let me start this main part of the talk with some general notation and abstract setting. So we fix a prime number P and a finite set of S of primes containing P. We denote by GS the Galois group of a maximal algebraic extension of Q unramified outside S and infinity. Fix some finite extension of QP, which will play the role of coefficients field, and consider two affinoid, simple affinoid disks. So two affinoid, first two affinoid rings R and A, and we consider the corresponding affinoids W and X. So we will always see them as closed disks. W plays the role of weight space, and X is covering of W, which is ramified at the center. And the ramification index in some parts of my talk can be arbitrary, but one can always assume that it is equal to 2. So we will denote by W the natural covering projection of X onto the weight space, and denote by X0 the center of X, which projects onto the center of W, so which is denoted by K0, and we will interpret it as the weight K0 point. Also, we can always consider points of integral weight, which we will denote by positive weight, which we will denote by X classical. And the main object of our study is a P-Adic representation with coefficients of dimension 2 or of rank 2 with coefficients in A. So we will systematically consider the specializations of this representation at different points. So sometimes we will consider V as an A module, specialized with respect to a point of x, at a point of x. Sometimes we will consider V as an R module and specialize with respect to a point of W. So in particular, if we specialize V at x0, so the specialization is of dimension 2 over E, but the specialization at k0 of V is equal to 2 times E, because X is ramified over W, and ramification degree is E. So we will consider VK0, the specialization at K0, as a deformation of the specialization at X0. So we have a tautological exact sequence. So we project Vk0 onto Vx0, and we denote by Vx0 the kernel. So if we assume that E is equal to 2, then Vx0 is isomorphic to Vx0. So we have 2 copies of the specialization of V at x0, Vx0 and Vx0 in brackets, and we have a deformation which is in the middle term of this exact sequence. Deformation provided by this big Galois representation V. Our principal assumptions are the following. So we will assume that at all classical points, the specialization of V at x is semi-stable at P, with hot state weights 0 and weight of x plus 1. We assume that there exists a crystalline subspace of in families at dimension of dimension 1. So there exists some function F of x such that the semi-stable module of V at x has eigenspace with respect to this action of Frobenius, and that this eigenspace is in general position with respect to the Hodge filtration on a semi-stable module. Namely, we assume that the intersection of this phi eigenspace with this filtration term is 0. Under these assumptions, we can triangulate the representation V. This is a general result of Liu and Kedlaya, Podhorst, and Xiao. Namely, if we consider the phi gamma module, which is of rank 2 over the big Rober ring, the phi gamma module associated to V, when this phi gamma module has a canonical submodule D of rank 1, which satisfies the following properties. Classical points, the specialization of D at X is satisfies this property. The crystalline module of dx is exactly this Frobenius eigenspace of semi-stable module of Vx. And at all points x of classical points x, with probably except x0, the phi gamma module dx is saturated in the phi gamma module of the specialization of V at x. So probably to be more precise, I should say that we eventually should shrink our disks to get these properties. So we now are interested in what can happen at the point x0, at the center of the disk. So two cases are possible. The first case, the case A, is a case where this property, the property C3, holds also at the point x0. In this case, dx0 is saturated and at x0. In some sense, the behavior of a family doesn't change. The case B is more interesting. If we assume that the intersection of these two spaces is non-zero, this means that they coincide because both are of dimension 1. When from general results about of P-Adic Koch theory of weak admissibility, we can deduce that the restriction of the specialization of V at x0 on the decomposition group of P at P is reducible. It decomposes into the direct sum of two vector spaces, two representations of dimension 1, which corresponds to roots of two eigenvalues of Frobenius phi acting on the semi-stable module. So we have this decomposition. We have associated decomposition of phi gamma modules corresponding to these representations. And in this case, the specialization of our triangulation D at x0 is not saturated. The quotient has a torsion, and d alpha is the saturation of dx0 inside the phi gamma module of the whole representation V. In this case, necessarily, the P-Adic valuation of alpha is equal to k0 plus 1, and the P-Adic valuation of beta is 0. So in the remainder of this talk, we will consider especially the case B, which is in some sense abstract setting for study of theta-critical P-Adic L-functions. So we assume that we are in a case B. Again, this means that the specialization of our big representation at x0, at the center of affinoid X, decomposes locally as a local Galois representation into the direct sum of two one-dimensional representations. We denote by alpha and beta the eigenvalues of phi acting on the crystalline modulus associated to these direct summands. And we consider V, the representation V, as a free A module of rank 2. And we will consider the specialization of V at x0, but also we consider V as an R module and consider the specialization of V with respect to the at K0, where K0 is the center of the weight space. When we have the following diagram, so the bottom line is tautological. So we consider the projection of this infinitesimal deformation of V at K0 onto the specialization at x0, and denote by Vx0 the kernel, which because the ramification is supposed to be equal to 2, so this kernel is as Galois representation isomorphic to Vx0. Next, inside of Vx0, we pick the direct summand, which corresponds to the eigenvalue alpha. And we take its inverse image in Vk0, which we denote by V tilde K0. So we denote by, so the kernel is the same, so we have this tautological diagram. So this means that we don't need to study the deformation of the infinitesimal deformation of the wall Vx0. We only want to deform, to study the deformation of this one-dimensional direct summand, which corresponds to the eigenvalue alpha. So from general arguments, it's easy to see that Vk0 tilde is a crystalline representation of dimension 3. Vk0 is of dimension 4 over E. Vk0 tilde is of dimension 3 over E, with hot state weights 0, K0 plus 1, K0 plus 1. So now we make some important assumption on the behavior of this deformation. So consider the following diagram. So the bottom line is just the exact sequence provided by the definition of V tilde K0. So V tilde K0 is the inverse image of V X0 alpha under the projection of wall deformation V K0 and V X0. And because we already know that V tilde K0 is crystalline, if we apply decrease, this gives an exact sequence too. Next, we have so we consider the crystalline model associated to dx0. To the I recall that D is the triangulation of our family, and we specialize it at x0. So we have an inclusion, which is in fact is an inequality, because the both spaces have dimension 1. So this is the same thing. But we can consider just the deformation of this triangulation dx0, which is dk0, which is of dimension 2. And the kernel, which we denote by dx0, is canonically isomorphic to dx0. So decrease dk0 is of dimension 2, and it is injected in the crystalline module of V tilde K0, which is of dimension 3. So our assumption is that the crystalline module of dk0 is in some sense in general position with respect to the hot state filtration and decrease V tilde K0. So we assume that V decrease dk0 is not contained in this filtration term of decrease V tilde K0. So one can remark that if this assumption fails, this means that VK0 tilde contains a two-dimensional subrepresentation with double hot state weight K0 plus 1, and V tilde K0 decomposes into the direct sum of two P-Adic representations, and this sense means that in some sense this deformation, infinitesimal deformation, which we consider is in some sense trivial. Now we will deduce some property from this assumption, from a property C4 about the filtrations on crystalline condition C4, about the filtration on decrease V tilde. So the following proposition is very easy to prove, just as some simple linear algebra, but it is one of key observations of this talk. So consider an element of decrease dk0. So when one can find a unique element in the crystalline module of Vx0 beta, such that their difference lives in the K0 plus 1 filtration of decrease of V tilt. So this property follows just from the preceding diagram. If we have an element here, an element D, which maps here, and if the condition C4 holds, we can always find an element here such that the difference will be in this filtration term. This provides the following following map from the crystalline module of a specialization of a triangulation D at x0 to the crystalline module of V x0 in brackets beta. So because this crystalline module is the crystalline module of a direct summand V x0 alpha, and by the same reason the crystalline module of Vx0 beta is isomorphic tautologically to the crystalline module of Vx0 beta. We have some map from the crystalline module over direct summand V alpha to the crystalline module of the direct summand V beta. So this gives some connection between two eigenspaces, two direct summands in the decomposition of V at x0. We have a decomposition of Vx0 at two one-dimensional representations, and using the deformation of Vx0, we construct a map from the crystalline module of a first term to the crystalline module of a second summand. Now we will use this observation to connect, first to construct and next to connect, to find connections between different P-Adic L-functions arising in this situation. So we will adapt Perrin-Riou's approach to constructing P-Adic L-functions using the large exponential map. We assume that we have another P-Adic representation V prime of rank 2 over A, together with an R-linear pairing between V prime and V. So this is some important point. Even if V prime and V are A-linear representations, we consider the pairing which is only R-linear, but not A-linear. However, we assume that this pairing satisfies the following adjunction property. So for any V prime in V prime and V in a capital V, if we act by X, I recall that X is the generator over A over R. This is a local parameter, corresponds to a local parameter on X. So we have the following formula. property implies that this pairing gives rise to a pairing between the specialization of V prime at x0 and the V x0 in brackets. Recall that V x0 in brackets is isomorphic to the specialization of V at x0, but this is a kernel of a natural projection on the specialization of at x0. Now we proceed by usual way. We can denote by gamma the cyclotomic Galois group of Q, by lambda the usual Iwasawa algebra, denote by HE the algebra of formal power series which converge on the open unit disk, and denote by HE gamma the corresponding big Iwasawa algebra. We also will consider the extensions by completed tensor product of this big Iwasawa algebra over E to R and A. So the local duality together with this pairing gives rise to a pairing between Iwasawa cohomology, local Iwasawa cohomology with coefficients in V and V prime 1 with values in this big Iwasawa algebra. This is again an R-linear map because the pairing between V prime and V is R-linear. Now we proceed to the construction of abstract P-Adic L-functions. We extend scalars formally, tensoring the second term here with A over R, and considering the pairing with values in HA gamma. Now, Perrin-Riou's construction of a large exponential map, or maybe probably better, its generalization by Berger and Nakamura, provides us with a map from the crystalline module of D, tensor HA gamma, over R, this is important, we work over R, to this Iwasawa cohomology. The general strategy of construction of P-Adic L functions by Perrin-Riou methods consists to choose some generator here and some special element here, special element which comes normally from the Euler system, and to consider this pairing, evaluate this pairing at these elements, and this gives some element here which can be seen as a distribution. Only in a classical setting, everything passes over either over the ground coefficient field E, or over some affinoid R, and A is equal to R. But in our case, we have in some sense two coefficient rings, R and A, and we should do something more subtle. In fact, the construction, the following construction is a direct analog of Belaish's approach to constructing two variable P-Adic L-functions in the critical, theta critical case. So we choose some generator eta of decrease D, and starting from this generator, we construct some explicit element, eta tilde, in the tensor product of decrease of D and A. So for any element Z in this Iwasawa cohomology, we define the P-Adic L-function LP eta tilde zeta as the pairing of Z, which is here, with exponential the image of a theta tilde under the exponential map. This gives us some element in H A gamma. We can evaluate this element in characters, finite or infinite characters, by a trivial wise way, and this gives rise to two variable P-Adic L-functions. What are properties of these P-Adic L-functions? Let's first consider what happens if we take an arbitrary point x over space x. Then the explicit construction of eta tilde implies that its specialization of x lives in the some one-dimensional E subspace of this module. I recall that W of x denotes the weight of x. The one-dimensional subspace, which is killed by the local parameter at x minus the point x. This means that, in fact, the specialization of our two-variable P-Adic L-function can be constructed by a usual procedure. So we consider the representation Vx, which is a two-dimensional representation over the field E, and the specialization of V at x, which is again a two-dimensional representation, and the exponential map from decrease of this submodule, which is again a submodule of rank 1 of the specialization of phi gamma module D at the weight k. So this is exactly classical Perrin-Riou's construction. To sum up this property, we can initialize our two-variable P-Adic L-function at x. We get some classical Perrin-Riou's style P-Adic L-function. Consider now the specialization at x0, at the center of x. When one can prove easily using just basic properties of Perrin-Riou exponentials that the values of this specialization at characters which are products of finite characters with character, the power g varies between 1 and k0 plus 1 is 0. So our P-Adic L-functions vanishes on the in the critical strip. We can next, following define the function L1, which is the derivative of this two-variable function with respect to x. The following, now we can formulate probably the main result of this talk. At least the main technical result of this talk. Recall our general setting. We have a big Galois representation V, which at x0 decomposes into the direct sum locally, again locally, not globally, locally decomposes in a direct sum of two representations of dimension 1, which correspond to two eigenvalues of Frobenius alpha and beta. The P-Adic valuations of alpha and beta satisfy this property. Using of this by the big Galois representation V at x0, we constructed by some version of Perrin-Riou's method a two-variable, first two-variable P-Adic L-function, and next one variable cyclotomic style P-Adic L-function, L1 in brackets at x0. We also constructed before in our setting some transition isomorphism between crystalline modulus of these direct summands. This construction uses essentially the infinitesimal deformation of Vx0 alpha provided by the representation V. Also, classical Perrin-Riou's construction provides us with the P-Adic L-function associated to, in fact, any element of decrease V beta. And we can take as such element the image of our element theta by under the this transition map. Then, so our main result says that in a critical strip, our P-Adic L-function satisfies the following interpolation property. It is related to special values of a P-Adic L-function arising from another eigenvalue of Frobenius. So the proof is an application of transition isomorphism together with some work with Perrin-Riou exponentials. What we can deduce now from this theorem? So I pass to applications, and here I will go very quickly because there are some technical points to explain, but I have time only to describe the idea. So come back to our situation. We have a new form S of weight K0 plus 2, a prime P which doesn't divide the level. We stabilize F with respect to two eigenvalues, alpha and beta of F. Consider the point of fix the stabilization, say F alpha, and consider the point x0 on the cuspidal eigencurve, which corresponds to the stabilization F alpha. Take a sufficiently small neighborhood of this point. When we have a big Galois representation, Vx, defined over with coefficients in the ring of functions on affine functions on X, big Galois representation which interpolates Denis representations. We can and do use the results of Andreato Jevita Stevens and the method of Belaïch-Chenevier to construct this big Galois representation in the neighborhood of x0. If the stabilization of F alpha is theta critical, when a difficult result of Breuil-Emerton says that locally Vx0 splits, and also that Belaïch's result says that X ramifies over the weight space. Conjecturally, the ramification index is equal to 2. This follows from, for example, from a conjecture of Janssen, which is much more general, but it is not proved. If we assume that this holds, that the ramification is equal to 2, we are in our scenario B. So we can apply our machinery, putting in our as ingredient the Belinson-Kata elements in families which live in global H Iwasawa cohomology. This provides us with a two-variable P-Adic L-function, which satisfies the following properties. If we specialize this L-function in a classical point different from x0, it interpolates up to some constant, multiplication by some constant, the cyclotomic P-Adic L-function of modular form at this point. If we specialize it at x0, Then our theorem says that if the condition C4 holds, I recall that this condition is a condition about the general position of our deformation of D, of triangulation inside the with respect to the Hodge filtration. Yeah, if this condition holds, then the special values of the derivative of our two-variable P-Adic L-function at x0 are related to the special values of a P-Adic L-function associated to another stabilization, to F beta, to the ordinary stabilization of our formula, our modular form F. So this gives another proof of Belaïch theorem, as well as another approach to the construction of Belaïch's P-Adic L functions. I think that I should stop here.
Thank you. Is there any questions or remarks?
I have a remark and a question. I don't know, I cannot put my video on, but that's probably because I'm not a co-host anymore. Do you hear me?
Yes, I hear. Yeah.
Okay, so the voice works. Okay, I have first a question before making like a remark. So when you say another construction, so for me, Belaïch's theorem is not, well, if it's not theta critical, then by definition, this is not et al. That's like a definition. And then by Breuil-Emerton, it's locally split. Belaïch's theorem is that it's smooth. And I think you use the smoothness, at least in your abstract setting, you're using that locally. It's like you take a square root of the parameter, right? You take like square root x squared equals y. So if the local ring is not normal, then Belaïch cannot construct the P-Adic L function. I mean, he's showing it's smooth, but it's unpublished. I mean, it's been a preprint for like almost 10 years. So my question is, are you proving that the eigenvariety is smooth at that point by a new method?
No, we use Belaïch's results, yeah.
Right, so I think, yeah, because you start by abstract setting, so you're assuming you're in a smooth setting. Okay, that was the question. So yeah, so you're using Belaïch. And my comment is, I think that if E is bigger than 2, probably you can retrieve your thing, because you can still just work with maybe what's killed by x squared. I mean, I feel like probably you can retrieve most of what you're doing for the application, even if it's bigger. And my other comment is, so this C4 condition, do you have some kind of a numerical criterion to test it on modular forms?
No. So this, I mean, this is a work in progress, and this is one of questions which should be studied. So I think that it can be proved, but certainly it is not an easy thing.
Okay.
Yeah, but yeah.
No, it's very good. Yeah, it's amazing. Yeah, it's really mathematics.
Probably I just about the method. Yeah, we use almost all techniques of main techniques of Belaïch-Chenevier, as well as results of Andreatta, Jovita, Stevens. So we need more tools. Because in some sense, Belaïch's approach, this is approach by, I mean, by Betti cohomology. Yeah, this is a Betti approach. We consider symbols which are correspond to Betti cohomology, and our approach is more étale and étale crystalline, which also involves some information about the RAM structure, about filtration. So we need, we need more properties to construct these functions, but also this is a K motivation. Yeah. So, for example, can we say something about the use in interpret these special values in terms of arithmetic invariance?
If not, I have a question. Do you have a conceptual explanation to the factor beta over alpha to the power n? Why it only depends on the conductor? It doesn't depend on the.
Please again.
At the end of your theorem, there's a relation between the P-Adic function, special value of the P-Adic function. So just this page, the last line, the equality.
Yeah.
And there's a factor beta to the power n over alpha to the power n.
Yes. Yeah.
And why this factor doesn't depend on the j?
This is the contribution of finite character. So only conductor. Yeah. So this
Is there any conceptual explanation to this fact? To this factor, why the reason?
I mean, this depends, because this formula appears also in Belaiche's context. If, for example, Belaiche obtained it evaluating modular symbols, and in Perrin-Riou's theory, this appears from the fact that you, when you take row part of, if you have a finite character row of conductor p power n, when you evaluate Perrin-Riou exponential, the row part of Perrin-Riou exponential, so this makes appear these powers.
So let's thank the organizer and ICTS for holding this amazing conference.